Okay. Last Tuesday we studied dehumidifier, and this dehumidifier is actually has one inlet and two exits. So we have inlet number 1, exit number 2, exit number 3. And what we do is we remove heat from this chamber, which is Q out. If it is a steady state dehumidifier, we can use a rate form. Instead of mass, we can use mass flow rate, m dot, and we can use q dot instead of q. Then we have a mixture of dry air and water vapor at the inlet number 1. So we have dry air, m dot of dry air at the inlet number 1, and we have the mass flow rate of water vapor, m dot of water vapor at the inlet number 1, because we have a mixture. We have a moist air entering the chamber at number 1. This moist air is a mixture of dry air and water vapor. Then, because of this heat transfer from the chamber to the outside, the temperature of this mixture is going to drop. And when it hits the dew point temperature, then we may have a condensation in the chamber, and water is going to be removed from this chamber at number 3. M dot of water. Then the remaining is going to leave this chamber at the exit number 2. So we have only water is removed. So we have dry air at the exit number 2, and we may also have remaining water in this air. That is m dot v number 2. So if we apply mass balance equation, unless there is a chemical reaction between the dry air and the water vapor, which is not likely, so the amount of dry air at the inlet number 1 should be the same as the amount of dry air at the exit number 2, because there is no dry air leaving at number 3. So one mass balance equation is m dot of A1 is the same as m dot of A2. You can just say m dot of A, because there's no difference between the inlet number 1 and inlet number 2 in terms of the amount of dry air. What about water vapor? This much water entering the system, and some of them is going to condensate. Some of them is going to condense and then leave the chamber as a liquid water at number 3, and the remaining water is going to leave at number 2. So this m dot of water at the inlet should be the same as the sum of m dot at number 3 and then number 2. So the mass balance equation for this water is going to be m dot of water vapor at the inlet should be the same as m dot of liquid water at the exit number 3 plus m dot of water vapor at the exit number 2. So that is mass balance equations for each component of this moist air. They are water vapor and dry air. What about energy balance equation? The energy balance equation, by the way, from this, since the amount of dry air is constant between number 1 and number 2, we can divide this equation by m dot of A, m dot of A, m dot of A. And since m dot is constant, we can say it is m dot of A number 1 or m dot of A number 2. Doesn't matter, right? So we can say this one is m dot of A number 1, which is okay, and this one is m dot of A number 2, which is okay, because m dot A is constant. Then, what is the definition of this humidity ratio omega? Omega is m of V divided by m of A. Then the left-hand side of this equation is going to be omega at the inlet number 1. So this one is omega at the inlet number 1, which is m dot of W divided by m dot of A plus omega 2. So m dot of, then this can be rewritten as m dot of W divided by m dot of A is omega 1 minus omega 2. So the difference between the humidity ratios is m dot of A per m dot of W per m dot of A. So if you want to determine the amount of condensate, we can use the humidity ratios between the inlet number 1 and inlet number 2. So this is the conclusion from the mass balance. Then what about energy balance? The energy transfer that goes into this chamber, then energy transfer leaving this chamber, they are equal. So what kind of energy transfer in? What kind of energy transfer are going into this chamber? So this is the control volume. This is the control volume. So what is, can you name any energy transfer that goes in? There's no heat transfer in. There's only heat transfer out, because in dehumidifier, we remove heat from this chamber so we can drop the temperature down to the dew point temperature. So there's no heat transfer goes in. There's no energy transfer by work goes in. There's only one energy transfer that goes in, that is the energy carried by this mass. So the total enthalpy at the inlet number 1. So the total enthalpy at the inlet number 1, H number 1, but we are using what? Rate form. So what is the rate of enthalpy? H dot. So H dot is the energy transfer goes into this control volume. Is there any other energy transfer that goes into this control volume? No, this is the only one. Then what about energy transfers leaving this control volume? We have a heat transfer Q. We have enthalpy at number 2. We have enthalpy at number 3. You can see the direction of each arrow. This one goes in, this one leaves, this one leaves, this one leaves. So there are 3 energy transfers out of these control volumes. So the first one is Q dot out, and number 2, the total enthalpy at number 2 per unit time plus the total enthalpy at number 3 per unit time. So this is the energy balance equation that we can use for this problem, dehumidifier. Then how can you determine this total enthalpy? We studied it, the total enthalpy, H, can be determined by NA times HA plus omega, humidity ratio, times HV. This is what we studied last week. So this is the first one that we studied for humidity ratio. This one is how you determine the mixture enthalpy. And we have H1. So it's going to be M dot A1, HA1, omega 1, HV1. Yeah, that's how you are going to complete this energy balance equation. So M dot A1, however, M dot A1 is the same as M dot A because there's no difference between M dot A1 and M dot A2. So I'm going to just say M dot of A without this number 1. Then HA1 plus omega, the humidity ratio 1, HV1, that is from this definition of enthalpy here, this equation. The only missing is M dot A1 because M dot A1 is the same as M dot A2. We can just say M dot A. And we have a dot on top of it. So we can add a dot on top of where? Just one place, and M dot is Q dot out plus. Now we have the total enthalpy at the exit number 2. So it's going to be, you just need to add number 2 in the subscript. But M dot A2 is the same as just M dot A. So I'm going to say M dot A HA2 plus omega 2 times HV2 plus the last one. H dot 3. How do you determine this H dot 3? Is it a mixture at number 3? No, it is just water. So we don't have to write this equation. It's going to be mass of water times specific enthalpy of water. Mass of water times specific enthalpy of water. And we have a dot on top of it. So I'm going to add a dot on top of it. So that's how you determine the energy balance equation for this dehumidifier. Then, why don't we divide by the mass of the dry air? I'm going to divide each term by M dot of dry air so that we can determine the specific energy rather than just energy. Divide by M dot of A, divide by M dot of A. Then here we can cross them out. What is this one? The difference in humidity ratio. Then can you rewrite this equation in terms of this rate of heat transfer? Move this one to the left-hand side. Move this one left-hand side and switch this way. Then we have Q dot of out divided by M dot A. So the rate of heat transfer per mass flow rate of dry air can be determined by HA1 minus HA2 plus W1HV1 minus W2HV2 minus omega 1, it's not W, omega 1 minus omega 2 times HW. So this is the energy balance equation. So that's everything. So based on this energy balance equation, let's, right here, based on this energy balance equation, let's solve this problem. Air at 30 degrees Celsius, pretty hot, 1.05 bar. So the pressure is greater than the regular normal atmospheric pressure. So it's one of the sunny days outside, and 80% relative humidity. That's impossible in Michigan unless it's raining. So somewhere in the coastal area, which is humid, too hot, so it's pretty bad. So let's run a dehumidifier. So dehumidifier, in this dehumidifier, we are going to remove heat from this dry, moist air. So at the exit, we have a much lower temperature, 15 degrees Celsius, 1 bar, and 95% relative humidity. Why humidity is higher than the inlet? Because when you decrease the temperature, the relative humidity goes up, right? And the rate of heat transfer by the refrigerant flowing in the cooling coil per kilogram is 100 kilojoule. So that is the rate of heat transfer per kilogram. And we are going to assume that there is no additional heat transfer. There is no change in kinetic energy and potential energy. We want to determine the flow rate of the refrigerant. So which means solve this equation and calculate the rate of heat transfer. If you calculate the rate of heat transfer, divided by 100, that's going to be the mass flow rate of the refrigerant, right? Because let's say we need to, to remove 200 kilojoule per second. That means we need 2 kilograms per second, right? So if you want to determine the mass flow rate of the refrigerant, you can determine the heat transfer rate from the dehumidifier to the outside and divide by the enthalpy increase of the refrigerant. So that's how we are going to solve this problem. Okay? So what we need to do first, we are going to determine humidity ratio, omega 1 and omega 2. What about this HA and HA at the inlet and HA at the exit? We know the temperatures of the air we know at the inlet, we know the temperatures of the, the air at the exit. So we can use specific heat to determine HA1 minus HA2. Then what about this, the specific enthalpy of water vapor? We can assume that the specific enthalpy of water vapor is close to the specific enthalpy of saturated vapor. We can do that when the humidity ratio is high. When this, the relative humidity is high, then we can assume that this one is close to the specific enthalpy of saturated vapor. And this one, this is the specific enthalpy of the water removed from this dehumidifier. Since the pressure is not that high, then how can you determine the specific enthalpy of liquid water? It can be either compressed liquid or saturated liquid, and there is no difference in the properties of compressed liquid and saturated liquid when pressure is not that high. Do you remember? Like, for example, in Thermodynamics 1 review, I told you that when you have a compressed liquid, phase change process number 1, if you want to determine its specific enthalpy, H. So in this case, HW. And there are two different ways. One is when pressure is high or equal to 2.5 megapascal, or the other one when pressure is lower than this value. Of course, the pressure is much lower than this value. So in that case, this HW can be determined by HW is the same as HF at the same temperature. So this is how we are going to determine the specific enthalpy of liquid water at number 3. So the only thing that we need to determine in this equation is going to be omega 1 and omega 2. So let's do that. How can we determine omega 1 and omega 2? We know the relative humidity. The relative humidity at the inlet phi1 is going to be 80%, which means 0.8. This relative humidity is PV over PG. And in this case, PG is the saturation pressure, P set at the given temperature. So similarly, this 0.8 is going to be PV over PG. In this case, PG is P set at the given temperature. What is the temperature? 30 degrees Celsius at 30 degrees Celsius. So what is P set at 30 degrees Celsius? At 30 degrees Celsius, P set is 0.04246. 0.04246 bar. Then from here, you can determine the partial pressure of water vapor, PV. And PV is, do I have it? 0.03397. 0.03397 bar. Then once you get this PV, then you can determine the humidity ratio. Just for your information, humidity ratio omega can be determined by 0.622 times PV over P minus PV. So humidity ratio omega 1 can be determined by 0.622 times PV over P minus PV. Do we have PV? Yes, this one is PV, goes here and goes here. What is the pressure at the inlet? 1.05. 1.05 bar. So we have everything. Can you determine the humidity ratio? Yes. Omega 1 is going to be 0.0208. What is the unit of this humidity ratio? There's no unit because humidity ratio is mass of water vapor divided by mass of dry air. But that's not it. We need to determine the humidity ratio at the exit number 2. If you look at this, we also need omega 2. So let's determine omega 2. We can use the same rule. Phi 2 is 95%. So 0.95, which is the same as PV over PG. Then what is PG? This PG is, did I turn on the mic? Oh, yeah, I did. You remember that I forgot to turn on my mic last Tuesday. So I found a similar video that I recorded last spring. I'm going to upload that. So that's okay, right? So P set at what temperature? What is the temperature? 15 degrees Celsius. 15 degrees Celsius. Then what is P set at 15? If you go there, table A2 at 15 degrees Celsius, P set is 0.01705. Then from here, you can determine PV. So what is PV? 0.0162. Bar. Then now we can determine omega. So whenever you convert between relative humidity phi and humidity ratio omega, what is the most important property? PV. So if you want to convert this one into omega, you need to determine PV, and we use this equation to determine PV. Once you determine PV, the humidity ratio equation is omega 2 is 0.622 times PV over P minus PV. Do we have PV? Yes, this number. What about the pressure at the exit? 1 bar, so 1. Now, can you determine omega 2? Yes. Omega 2 is 0.0102. Any question up to here? It's not difficult, right? The information given in the problem is relative humidity, but whenever you use the energy balance equation, you need humidity ratio. So what we did, just converting, the relative humidity values to humidity ratio values, omega 1 and omega 2. Once you find omega 1 and omega 2, now you can apply energy balance equation. Where is that energy balance equation? Right here. Energy balance equation. So now we know omega 1, omega 2, omega 1, omega 2. The only thing that we need to find is going to be the specific enthalpy values of air, of water vapor, of liquid water. So let's do it. So how do we determine the specific enthalpy change of dry air, if you have a dry air, you can use specific heat, right? Or if you want, you can use ideal gas properties of air in table 822. There's no problem. But if you want to use a specific heat this time, because the last time we used the ideal gas property table in the previous problem, so this time we can use a specific heat. So you can experience both methods to find these values. So H1 minus H2 is Cp times T1 minus T2. Wait, should we say TA1? There's HA1. Should we say TA1? Why we say HA1? Because HA1 is different from HV1. What about TA1 and TV1? They are the same. Remember, when you have a mixture of gases, they share the volume, they share the temperature. So there's no TATV because temperature is the same. Temperature is equal between the air and water. Volume is equal between air and volume. When we say this much volume, it has air and water vapor. Just for your information, this is a mixture. When we study them in thermodynamics, we assume that air occupies the entire volume. So the volume of air is going to be this one. Volume of vapor is also this one. So there is no VA, VV. You don't have to separate them. There is only one V. So only one V is V of dry air is V of water vapor. Make sense? What about temperature? Oh, this one is 20 degrees Celsius. Then the temperature is going to be 20. That is the temperature of air. That is the temperature of water vapor. So there is no difference between dry air and water vapor. So when we talk about volume and temperature, we assume that each occupies the entire volume and they share the same temperature. Then when is different? Another blue and black. I don't know why I changed it. So there's only blacks here. Oh, there's a red. But when we talk about pressure, that's when it is different. When I say the pressure is, oh, it doesn't work. Thank you. So when we talk about pressure, if it is 100 kilopascal, then that's different. The total pressure, T, is 100 kilopascal. This one is not the same as the pressure of water vapor. That is not the same of pressure of dry air, pressure of water vapor. They're not the same. They don't share. Instead, this pressure is going to be pressure of water, dry air plus pressure of water vapor. Okay? So when we talk about pressure, volume, temperature, we don't distinguish air and water vapor for volume, temperature, but pressure is different. Okay? What about the mass? Of course, it's different. If the total mass is 1 kilogram, this is going to be mass of dry air plus mass of water vapor. They're not the same, okay? So only the properties, only temperature and volume, we assume that they're the same, okay? So that's why There is no TA1, TB1. It is just T1. It is just T2. There are only two temperatures in this inlet and the exit. One temperature for the inlet, one temperature for the exit. So then what is this aspect heat? We can use 1.005 kilojoule per kilogram Kelvin multiplied by the inlet temperature, 30 degrees Celsius. Sorry, let me go up. I need a larger screen. T1 is 30 degrees Celsius. The temperature of dry air is at 30 degrees Celsius. The temperature of water vapor is also at 30 degrees Celsius, minus the exit temperature, 15. So that's how you determine the change in specific enthalpy of dry air. Yes. Put on a table. Here, at 300 Kelvin. To be exact, to be accurate, you need to determine the specific capacity value at the average temperature between the inlet and the exit. That is close to 1.005. I think it's okay. Then we already found this relative the humidity ratios. They are here. Humidity ratio omega 1 is going to be this number, 0.0208, and omega 2 is this number, 0.0102. What about here? Yeah, we know them too. 0.0208, 0.0102. Then what else? We need to determine HV1, HV2. When relative humidity values are high, we can assume that these are, the similar to the specific enthalpy of saturated vapor, which is Hg. This one is also Hg. Then where can we find Hg? The one at the inlet, what is the temperature at the inlet? 30 degrees Celsius. Hg at 30 degrees Celsius. What is the exit temperature? 15 degrees Celsius. Hg at 15 degrees Celsius. So where is Hg at 30 and Hg at 15? Hg is here. This one is at 15, this one is at 30. So this one is here. 2556.3. This one is here. 2528.9. The last one is the specific enthalpy of water, liquid water. Then how can you determine this value? We can use this relation. If you have a compressed liquid, of course it's a compressed liquid, right? It is after condensation. We have a liquid water. And the properties of this liquid water can be approximated by the properties of saturated liquid, HF, at the same temperature. Then what is the temperature of this liquid water? Condensate exits in a separate stream, which is exit number 3 at 15 degrees Celsius. So this one is H of saturated liquid, HF, not G, at 15 degrees Celsius. And where is it? at 15 degrees Celsius. HF is here, so 62.99. 62.99. And if you do the calculation, you can determine Q dot over M dot of A. That is 400. How much is it? 41.8. 41.8 kilojoule per kilogram. So this much rate of heat transfer per dry air is required. So Q dot out per the mass flow rate of dry air is 41.8 kilojoule per kilogram. And each kilogram of refrigerant can remove the enthalpy of 100 kilojoule. So to remove 41.8 kilojoule, how much refrigerant do we need? Divide by 100, we need 0.418 kilogram of refrigerant required per kilogram of dry air. So that is the answer. Because each kilogram of refrigerant can remove 100. So 0.418 kilograms of refrigerant can remove 41.8 kilojoules. That's how you analyze a dehumidifier. Yes. Yes. Oh, it doesn't matter because it's going to be multiplied by the difference in temperature. So difference in degrees Celsius and difference in Kelvin, they are the same because you are going to add 273, add 273, they're going to be canceled. So the specific capacity unit is the Kelvin, the temperature is the exchangeable. You can use Kelvin or degrees Celsius. They're both okay. Any question about gas mixture? So that's everything for gas mixture. Some people like to use this psychrometric chart to understand moist air. Looks pretty complicated. And this is a instruction how to use the psychrometric chart. And this is just for your information. It won't be in your exam. Okay. Pretty easy, if you want to find these numbers, you can just go into the table and find the right location. But I recommend you use property table as we use energy balance equations and entropy balance equations rather than using the chart. So that's everything about moist air. And we are going to study the second part of this thermodynamics 2, conversion. So this is a rapid oxidation. That means that the carbon becomes carbon dioxide or carbon monoxide, and hydrogen becomes water, sulfur becomes sulfur oxide, and etc. So when we say it's going to be fully oxidized, then we assume that it's a complete combustion. It's a complete combustion when we have a complete oxidation, which means that the carbon becomes carbon dioxide and hydrogen becomes water, 2H2O, and sulfur becomes sulfur dioxide, and etc. etc. And if we have smaller numbers of oxygen, we say it is incomplete. So to have a complete, to make it complete, these are how these, the chemicals are oxidized. And if you have a smaller numbers, instead of SO2, you get SO. Instead of CO2, you get CO. That means it is incomplete. Then how can we study this process? We need to know what is called balanced reaction equation. So whenever there is a chemical reaction, we need to be able to complete this balanced reaction equation. And this is on a molar basis. 1 mole of methane is going to react with oxygen and becomes carbon dioxide and water. So we are going to study how to determine this balanced reaction equation first. That is the first part. So first part is going to be how to use this balance, how to determine this balanced reaction equation. And second, we are going to complete this energy balance equation. Energy balance. And finally, we are going to study entropy balance. So these are the 3 items that we are going to study in this chapter. So let's determine the balanced reaction equation for some simple substance, in this case, methane. CH4 is methane, and when we have a when this one has a reaction with oxygen, going to react with oxygen, but I do not know how many moles of oxygens are required to have a complete conversion. Then if it is complete conversion, complete combustion, then we have CO2 and H2O. If it is incomplete, then we may have carbon monoxide and CO2 and H2O. Or even C or H, etc. So when you want to determine balanced reaction equation, you need to determine, are we going to write a complete balanced reaction equation or incomplete balanced reaction equation, okay? So let's say that, that we want to determine this complete balanced reaction equation, then how can we do that? It's pretty simple. CH4 is going to react with oxygen, but I don't know how many. And we know it becomes, C becomes carbon dioxide, and this H becomes water. So what we need to do is that we need to determine how many moles of each component is required to have a complete reaction with 1 kilomoles of methane. So when you see there's no number in front, you can assume that it is 1 kilomole. Then it's pretty simple. It's a simple mathematics. So we have, let's talk about, the carbon first. There's a carbon in this methane. There's a carbon in this carbon dioxide. So there's no other carbons here in this equation. So if we have 1 carbon, 1 times C, 1 carbon, you can make 1 carbon dioxide. So that's how you can determine the number of moles of each component. And what about hydrogen? We have how many hydrogen atoms here? 1 times 4. We have 4 hydrogen atoms. So to have 1 molecule of methane requires 4 hydrogen atoms. So this one has 4 hydrogen atoms. And how many hydrogen atoms required to have 1 molecule of water? 2. So if you have 1 molecule of methane, you can create 2 molecules of water. Make sense? So there's a 2. And the last one is going to be oxygen. How many oxygens in this carbon dioxide? 1 times 2. 2 oxygens. And how many oxygens here? 2 times 1. 2 oxygens. So in total, how many oxygens? 4 oxygens. Then each oxygen molecule has 2 oxygen atoms. So if we have 4 oxygen atoms, how many molecules of oxygen? 2. 2. So that's how you determine balanced reaction equation. 1 kilomole of methane can react with 2 kilomoles of oxygen. It can create 1 kilomole of carbon dioxide and 2 kilomole of water. Okay? Pretty simple, right? What about if we have air instead of oxygen? Air is considered to be 21% oxygen, 79% nitrogen. So 21% oxygen, 79% nitrogen. So what is this ratio? Is it mass ratio? No, this is molar ratio. 21% by mole is going to be oxygen. 79% by mole is going to be nitrogen. So what is the ratio between? It's going to be 21 to 79. That means each mole of oxygen, there are 3.76 moles of nitrogen. So let's determine this balanced reaction equation for this methane, this time with air. This time, this 1 mole of methane is going to react with water, and not, air, not this oxygen. So we have oxygen and nitrogen together. And what is the ratio between oxygen and nitrogen? 1 to 3.76. So each mole of oxygen, we have 3.76 moles of nitrogen are there. Then we have only one carbon here, so we can create one carbon dioxide. We have 4 hydrogen atoms here, so we can create 2 water. And we have nitrogen is not going to react. Nitrogen present in the air is assumed inert. That means that it's not going to react. Is it right? In general, it is right. However, in a certain condition, this one is not right. When is that certain condition? When pressure is extremely high. When do we have a combustion when pressure is extremely high? When you drive a diesel engine, the pressure is extremely high. That's how we increase the efficiency, by increasing the compression ratio. If you remember Thermodynamics 1, in that case, this nitrogen becomes nitrogen oxide. So it's going to react with oxygen. That's going to be one of the reasons for the air pollution. Anyway, in this Thermodynamics 2, we assume that nitrogen is not going to react. So this 3.76 nitrogen is going to be in the product, nitrogen. Oh, by the way, the left-hand side of this balanced reaction equation is called reactant. The right-hand side are products. Okay. Then we have 1 mole of carbon dioxide, 2 mole of waters. So how many moles of oxygen required? So this one, we have 2 oxygen atoms. This one we have 2 oxygen atoms. Together we have 4 oxygen atoms, and each molecule has 2 oxygen atoms. So how many moles? 2. So how many moles of nitrogen in the reactant? 2 times 3.76. So how many moles of nitrogen should be in the product? 7.52. So that's how you determine the balanced reaction equation for methane that is going to react with air, not just oxygen. So the first balanced reaction equation is for oxygen. The second one is for air. The ratio of the amount of air in this reaction to the amount of fuel, so this ratio is called the air-fuel ratio. And in this case, the air-fuel ratio is going to be on a molar basis. So we have a bar on top of it. So if you change it to mass basis, it's going to be, the just AF without bar. If you add a bar, that means that on a molar basis. If you don't have a bar, that means on a mass basis. And how can you determine this air-fuel ratio on a molar basis? It's pretty simple. How many moles? 1. How many moles of air? 2. So 2 over 1. Oh, wait. This is air. So we have 2 moles of oxygen and 7.92 moles of nitrogen. So altogether, 9.52. Okay? So we studied the balanced reaction equation for oxygen, the balanced reaction equation for air. Then let's talk about balanced reaction equation for 150% theoretical air. So when we have this reaction, rapid reaction, that means that, the reaction with oxygen, we may need more than, the more oxygen than required to make sure that it's going to be a complete conversion. So then how can we determine that? We can start from here. So this is the balanced reaction equation with 100% theoretical air. If we have 200% of theoretical air, then this equation is going to change. So if we have 200% theoretical air, this number is going to be multiplied by 2. So this balanced reaction equation becomes 1 methane is going to react with not 2 but 4 oxygen and nitrogen together, and the ratio between oxygen and nitrogen is going to be 1 to 3.76. And since we have a carbon, it becomes carbon dioxide, and we have a hydrogen, so it's going to be water, and we have some leftover oxygen, and we have some leftover nitrogen. Then we only have 1 carbon here, so 1 carbon dioxide. We have 4 hydrogens here, so we have 2 molecules of water. Then you have 1, 1. So how many oxygens here? 2 plus 2, it's 4, but we have 8, so 4 are left. So 4 oxygens to be here, and each molecule of oxygen has 2 oxygen atoms. So 2 and 4 times 3.76. Four times 3.76, the 15.04. 15.04. That's how you determine the balanced reaction equation. Yes. Oh, 200% air. 200% air. Air. Then let's make another modification. What about 50% of this methane has been reacted with oxygen? Only 50%. Then this one is going to be even more complicated. So now this time still 200% air, but only 50% of methane is going to react with oxygen. Then this balanced reaction equation becomes CH4, the methane, plus 4 times oxygen plus 3.76 nitrogen, but this time only 50%. So 0.5 moles of methane is going to be in the product. 0.5 methane. And how many, the moles of carbon dioxide? Only the half. 0.5 CO2 plus H2O plus. Then now it's going to be complicated. So only half of them. So let's count the number of oxygens. So we have 0.5 times 2, 1 oxygen. We have 1 oxygen. So we only have 2 oxygens here. However, we have 8 oxygens. So how many oxygens left? 6. And each oxygen molecule has 2 oxygen atoms. So 6 oxygen atoms can create 3 oxygen molecules. And what about nitrogen? It's an inert gas, so they're not going to react. 15.04 nitrogen. Let's make it even more complicated. So this time, we have 200% air, and only 50% was reacted. And we have 20% of this one is, 50% of this one is carbon monoxide. So 50% carbon monoxide. Is it good or bad, by the way, compared to this one? We know that both are not good, right? Global warming. And what is the problem of this one? When there's a fire in a house, many people die because of this, rather than actually burned by fire. Because this one has a more attraction to your lung. So the lung cells, they attract carbon monoxide rather than oxygen. So your entire body is going to be filled with this one, rather than oxygen. So that's why, when people, rescued from the fire site, they need to have a high pressure oxygen to get rid of this one. Anyway, that's not thermodynamics, but good to know, right? So this time, methane, 4 times oxygen plus 3.76 nitrogen is going to be 0.5 methane, and we have 50% of this one. 0.25 carbon monoxide, 0.25 carbon dioxide, and water, and oxygen and nitrogen. One thing for sure we know is this nitrogen is kind of laid back down there, so that don't change. 15.04. It's like those up there overseeing this one. Oh, there's a combustion. I'm nitrogen, so I don't care, right? No, not funny. So carbon is okay, 0.5 carbon plus 0.25 carbon plus 0.25 carbon. So it becomes 1 carbon, so no problem. What about hydrogen? 0.5 times 4, so 2 hydrogen, 2 hydrogen, so 4 hydrogen, so hydrogen is okay. So the problem is oxygen. So 0.25 oxygen, 0.25 times 2, 0.5 oxygen, 1 oxygen. So altogether, how many? 1.75 oxygen. So we have 1.75 oxygen. How many oxygens here? 8 oxygen. So how many left over? 6.25. 6.25. And each oxygen molecule has 2 oxygen atoms. So how many oxygens do we have in the product? 3.125. So that's how you complete the balanced reaction equation. A little more complicated? I think that's enough, right? So if I give you a condition and tell you to determine the balanced reaction equation, can you do that in the exam? Yes. This is the starting point. Whenever you have, you want to, use energy balance equation or entropy balance equation, you need to be able to determine this balanced reaction equation. So please practice, how we can determine the balanced reaction equation. So that's everything up to here. Then before we actually solve a problem together to determine the balanced reaction equation, one thing you need to know more is going to be then when we, actually perform an experiment, how can we determine the balanced reaction equation for that experiment? We use something called dry product analysis. It's a mass spectrometer. You can analyze, how much, each, the gas component is in the product. We have that kind of tools here in campus. Yes, room 103. There's a gas spectrometer. 103. The room, the room on that side, in the corner. Have you been there? Yeah. 105. So there is a gas spectrometer, and my lab here, 127, it also has a spectrometer, but it's not gas spectrometer. So that one is only for solid. So we can measure that, but the problem is that these gas spectrometers can only measure the amount of gas. So if you look at the balanced reaction equation, most of them look like a gas, but there's only one is not gas. What is it? What is not gas? This one. There is no guarantee that this one is a gas, right? So those, the spectrometers cannot measure the amount of water. So the amount of water is what? You need to guess. You need to calculate by completing this balanced reaction equation. That is called dry product analysis. So this dry product analysis can only give you the amount of gas component in the products. So if this ethanol is going to burn with air, we know ethanol has C to H5, actually 6, because there's one more H. OH is going to react with air, so we have oxygen, nitrogen. So what are we going to get? Carbon becomes carbon monoxide, so it's incomplete. Carbon monoxide and carbon dioxide and nitrogen. And what else? Water. So the ratio is going to be 3.16%, 16.6% carbon monoxide, 80.24% is nitrogen. Then, whenever you see this percentage, the first question you need to ask, mass basis or molar basis? Dry product analysis always give you a molar analysis, so it's going to be mole basis. So you can assume that we have 3.16 moles of carbon dioxide. I'm sorry, just 16. 16.6 moles of carbon monoxide, 3.16 moles of carbon dioxide, and nitrogen, 80.24 moles of nitrogen. We don't know about this number of moles here. We know this one is 3.76, and we don't know how many moles of water. So you need to determine this one, this one, this one. So this is a typical problem you may see in your exam, and this is the first step whenever you want to use energy balance equation and entropy balance equation, because we need to know these numbers. Okay, so that's everything for today, and the next class we are going to study how to apply energy balance equation and entropy balance equation once we complete this balanced reaction equation. That's it. Thank you.